Okay, so the internet isn't working, so I'm in class with Luke and Kenny, and we're going to try to have class like this, and I'll post it as a video. So if you're actually watching this, it must have worked. So today is Wednesday. The homework tonight, you're going to have one Khan Academy quiz. You also have questions. There's like 8 to 10 questions that are based on the mock exam you did last week. And these are the hard questions. So if you struggle with these, that's okay because they're the hard questions. You get multiple attempts, and feel free to message me and ask any question you want, just so you can better understand how to do those types of questions. Today, we're going to be looking at what's called a chi-squared test for homogeneity. There are 3 different chi-squared tests. We talked about a goodness of fit test yesterday, and this is a new chi-squared test. So we're going to compare 2 different brands of gummy bears. So the first brand is Haribo, and the next brand was the Target Off brand. So I'm just going to call it Off brand. And the students in the class have already counted red, orange, yellow, green, and white. And the students counted in our sample 44 red Haribo, 15, 23, 26, and 16 for a total of 124 Haribo gummy bears. And the off-brand was 16, 17, 14, 29, and 24 for a total of 100. And then the total red between the 2 brands was 60, and then 32, 37, 55, and 40 for a total of 224 gummy bears. So what we'd like to know, those are called our observed counts. What we'd like to know is, does the Haribo brand, is that color distribution the same as this Target Off brand? So you can see some differences here. It looks like Haribo in our sample had a lot more red, and then for the Off brand had more white or pineapple flavor. So a couple questions. How many samples do we have? We had 2 samples, 1 from each brand. So that gives us 2 populations that we're looking at. Anytime you have 2 populations or 2 samples like this, you won't be using a goodness of fit test, but you'll be using a different chi-square test. How many variables are we examining? We're only examining 1 variable. The brands themselves isn't really like a variable that we're examining, it's the color. So we have 1 categorical variable that we're examining, and that's color. So yesterday with the goodness of fit and Skittles, we had 1 sample in 1 variable. But today we have 2 different samples, 2 different brands, and 1 variable. So what are the statistical explanations for the difference that we observe? So like this difference here, why would Haribo have so many more red than the off-brand? So any thoughts from the class?
It could be some sort of like marketing reason.
Okay, so maybe the 2 brands decide to market differently, so they have a different color distribution. So I'll put that as number 2. The 2 brands, one explanation is the 2 brands have different color distributions. And that's why we see the differences that we see. Maybe that's marketing. You know, their market analysts have determined, oh, we want to have a lot of red because when people see red in the bag, that's, creates pleasurable thoughts that I really want to eat these gummy bears because of all red is my favorite color, whatever marketing it is. What's another possible reason or explanation why there are differences that we see in these different colors?
It could be sampling variability.
Yeah, exactly. It could be sampling variability. So we could say the two brands have the same color distribution, and the difference is just due to sampling variability. So those are our two explanations. One explanation is they have the same color distribution. We see differences like this 44 red, 16 red for the off-brand. That's just due to sampling variability. If we had different packages that we examined, then maybe that'll even out and be roughly the same count. But otherwise, another explanation is maybe they're different just because they're different. The color distributions for the populations could be different. So those match the hypotheses for this test. Just like we did yesterday, we'll often write them in words, not symbols. So we would say the two brands have the same.
Is the null always this, like they'll have the same?
Pretty much, yeah. The same color distribution. Well, Kenny, it depends on what test you're doing. The one from like chi-squared and then today's chi-squared, you'd use the same and different. But then tomorrow's, it's a little bit different, but it's not going to be complicated, so you'll be able to figure it out.
But you never use, like, it'll be different in the null.
Oh, right, yeah. Yeah, for sure. It's always something like equal to or the same in the null. And then the alternative is that the two brands have different color distributions. So basically chi-squared tests are always like a not equal to, whereas the same is an equal to, that kind of idea. Now it doesn't end up being two-sided because of the type of distribution that it is, but different is like a not equal to. Okay, so we're going to use a chi-square test to test if there's a difference between the two populations, the two types of brands. But first we need to calculate the expected counts. So let me write the totals again, just the totals, not the observed, but the total numbers are these. And then 40. And then we have 124, and we have 100. Okay, so those are the totals. Oh, let me write a Haribo up top and the off-brand. And we had red, orange, yellow, green, and white. Okay. So let me talk you through what it would look like to calculate the expected count for this cell, red Haribo. So the thinking is, if there were no difference between the two types of brands, then we would expect 60 out of 224, which is what percent? 60 out of 224. That's 27%. We would expect 27% of each of these to be red if there's no difference. So we would do 27% of 124, which is 33.2. That's 27% of how many total Haribo we had. And then likewise, we do 100 times that 27%, and we would get 26.8. So roughly 27, but 26.8.
How can you get 26.8 instead of 27?
Yeah, I had rounded the 27. It's really 26.8%.
Okay.
Yeah, exactly. Whoa, what happened? So that's how you calculate an expected count. So anyone in the room like to figure out what do you think you would do to calculate this blue box here, the orange Haribo expected count?
Do 32 divided by 224 and then multiply it by both the sample sizes.
Perfect, yeah. You would take 32 divided by 224. That's, I'm going to round it a little bit. That's roughly 14%. You would expect 14% orange in Haribo and 14% orange in the off-brand. So that's going to be 32 divided by 224 times 124 is 17.7 for Haribo. And then 32 divided by 224 times 100 is 14.3 for orange. And then we can continue that pattern. We have the next one we would have is 37 over 224 times 124, 20.5. And the other one, using subtraction here, I think should be 16.5 because it needs to add the 37. So I think that's 16.5. And then 55 over 124 times 124 is 30.4. And the other one should be 24.6, since they should add to 55. And then 40 over 224 times 124 is 22.1. The other one would be 17.9, I believe. So these are our expected counts. So the basic formula that we just used, there is a formula for expected counts. We took, so the expected count, we took the row total that the cell was in, so like that red Haribo, the row total was 60. We divided by 224, and then we multiplied by 124, the column total. So we would have the row total divided by the table total. That gave us the percentage of a certain color. And then we multiply by the column total. So that's the formula for an expected count for a two-way table. This was a two-way table. We have the brand as one characteristic and then the color as the variable that we're analyzing. So those are the expected counts. We need those to perform the test as well as to check conditions. So on the next page, and just for people at home, these were the a picture from last class. This side, that's the Haribo that they were looking at in third period, and then this side is the off-brand from Target. Okay, so we already wrote the hypotheses, but just to remind you, the four-step process, you would start with hypotheses. So you could just put see previous page. We already wrote the hypotheses. We'll use an alpha level, a significance level of 5%. The name of the procedure we're going to use is a chi-squared test for homogeneity. It's called homogeneity or homogeneity, the prefix homo being the same. So we'd like to know, are the distributions the same? Are these two distributions the same? So that's one way to remember homogeneity or homogeneity of proportions. Are the colors the same in these two separate distributions? So that's the name of this chi-square test. So we've had goodness of fit and we have homogeneity. The conditions we have, we're assuming that we took a random sample, 2 random samples, 1 from each brand. I don't know if that's necessarily a good assumption. I hope that the bags that I purchased were representative of the color distributions for each brand. On the AP exam, you'd be told that you had random samples or random assignment to treatments if it were an experiment. The independent condition, since we're sampling, we would need to make sure that the sample or the populations are large enough. And there's a lot of gummy bears in the world, so I don't think that's going to be an issue. So there are more than 10 times our sample for Haribo and 10 times the off-brand gummies. So the population sizes, I'm sure, are humongous. So taking a sample out of those populations aren't going to change the characteristics of the population at all because they're huge. And then the last condition is the large counts condition or the expected counts condition. So we need all the expected counts to be what? That's the same as yesterday, same condition. Greater than 5, yeah. So let's take a look at our expected counts. And are all the expected counts greater than 5? Yeah, for sure. The easiest way to check the condition is to find the smallest one, this one, and to state the smallest is 14.3, which is greater than 5. So if the smallest is greater than 5, they all must be greater than 5. So 14.3 was the smallest. So the large counts, we would say the smallest expected count Did I say 14.5? Is that what it was? Yeah, I already forget. 14.3. Okay. Is greater than 5. So all the conditions are met. The large count condition tells us that our test statistic will follow a chi-squared distribution with a certain degrees of freedom. Again, I just want to point out that there is no normal condition. So do not mention the normal condition. That's because chi-squared is not a normal curve. It's a right-skewed distribution. So we should not have any normal condition mentioned. The specific formula we're using for our chi-squared test statistic is the sum of all these components. You do your observed minus expected squared divided by your expected for each cell in the table. Now that's going to be a lot because we have 10 cells to do, and that's quite a few. Let's just show the first one, chi-squared equals, and then we'll use our calculator to find the test statistic. So the first cell is going to be, we're going to have 44 minus 33.2. So let me write that down. 44, 33.2. 44 minus 33.2 squared divided by 33.2. And we would continue that until we end with whatever the chi-squared test statistic is. So plus ... So let me show you, if you have your calculator, Sandy. Let me show you how we're going to use a calculator. And I think, at least from the past, students really like this one. So I don't want to get your hopes up or anything, but students really like this, using this test option on their calculators, because it does a lot for you. So if you go to your calculator, which I figured how to take a picture on my calculator. Oh, not that one. If you go to this option, if you hit second, and then this button is the matrix option. And it should look something like this. You have names, math, edit, and then all these on the side, these are matrices. This is matrix notation, has little brackets around the letter. So that's matrix A, this is matrix B. Now you might not see this in your calculator, but we're going to change that soon. So if you scroll to the right over to edit, we're going to input our observed counts into matrix A. So that looks like this. So select edit. You have number 1. You could also type number 1 once you get to edit, hit enter, or select number 1. And that will take you to a menu that looks like this. So this is matrix A. There's matrix A. And you probably have numbers here and here. What we need is to tell the calculator the dimensions of our matrix. The matrix is just this table that has all our observed counts. So we need to tell it that there are 5 rows. The rows is always first. 5 rows and 2 columns. So if you type 5 here and hit enter, and then type 2 here and hit enter, it will make a 5 by 2 table. And then you type the numbers in the table. So why it doesn't? What do you mean? Sorry.
Like yesterday with the other test, it like automatically had a table. It happens when you have to do the extra.
Oh, because it's more versatile. You could have 10 different brands of gummies that you're comparing.
Okay.
And then you could have 6, 7, 8 different colors or whatever. So it lets you have the flexibility of however many rows and columns you want, whereas a list is only just one list of like one variable. Yeah. And then there are special operations that matrices can do that you learn in Math 4, but we don't really use those operations in this class. We just use the function on our calculator. So edit, I want a 5 by 2, and we had 44. And then once you hit enter, it'll jump to the right, and then it'll jump down to the next row after that, as you can see. Okay, so once you have those, it should look like this. Those are our observed counts. Oh, well, not exactly, but was the numbers from last period. So it'll look like this. Those are the observed counts. You can double check that I didn't make any typos. You want to check yourself too. Okay. Do not include the totals. You're only including the observed counts. The calculator can handle the totals on its own. You don't have to tell it the totals. Okay, so from there, we're going to go to tests, like you've done before, the test menu, and you're going to select the chi-squared test, not the GOF, but just the chi-squared test.
Are you going to like stat?
Yeah, so you go to stat, and then over to tests, and then scroll down or hit the up arrow because it's near the bottom anyway, so you can go from the bottom up. And that's chi-squared test. So stat over to tests, chi-squared test. And then it looks like this. The calculator is asking, are both of you good? You're on that menu?
Yeah.
Okay. So the calculator is asking, where did you put your observed counts? And we put them in matrix A, so that's good. Don't have to change anything. Where did you put the expected counts? Well, we never type those in, but the nice thing is we don't have to. So just leave this. You don't have to change anything about this screen. And then select calculate. And you should get an answer of, take a photo. You should get that chi-squared. Did you get that?
Yeah.
Good. That chi-squared and that p-value with 4 degrees of freedom. So 14.7 and a very small p-value. So let me go back to this page in the notes. So this chi-squared value was, what was that, 14.7?
Yeah.
This equals 14.7. And that is acceptable work on the AP exam to show the first term plus dot 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 gives you the test statistic from your calculator, which is really fast, much nicer. So the picture that we just had, our test statistic, our distribution is right skewed. Our test statistic is way out here, 14.7. And I know it's way out there because our p-value is really small. Our p-value we found was, excuse me, 0.005. And our test statistic was 14.7. The calculator showed us the degrees of freedom being 4. The formula that was used to calculate that is number of rows minus 1 times number of columns minus 1. And I'll show you in a second where that formula comes from. But we had 5 rows, 5 colors, and we had 2 brands. So that would be 4 times 1 is 4 degrees of freedom. So this is a chi-squared distribution with 4 degrees of freedom. Where that formula comes from, let me just take a quick detour to explain why the degrees of freedom formula is what it is. Let's say we have 5 categories here, just making some things up. Let's say we have 2 categories here. We'll say like, I don't know, X and Y. And we have these totals, making some numbers up. Let's see, that's a total of 100, 200. Oh, that's nice. Let's say we had 50 of these and 150 of these. Okay, so again, I'm trying to explain where the degrees of freedom formula comes from here. So let's say I tell you that there are 2 in this cell. So you have these different cells here. Do you know what all the other cells have to be if I told you that top one was 2? Can you like logically deduce what all the other numbers are? You can figure this one out, but because it has to add to 20, but you can't figure out any of the others. So if I told you this one was 5, would you be able to figure out all the other cells? Not yet. You can figure out, right, this is 18 and this would be 25, but you can't figure out the other ones. You would have to have 4. So I'm free, degrees of freedom, I'm free to pick numbers until I've gotten to 4 numbers. And after that, now I can't just go freely picking numbers, because these values have to be whatever, adds up to the totals. 34, 49. I don't know if they're actually gonna, like, if all of them will add up nicely, but and then what's this? 2, 7, 8, 14. So this would be, I think, 36, something like that. And then you can do the math and figure out the other ones. But I had 4 degrees of freedom. I had 4 numbers that I could pick. And then after that, I can't just go picking numbers because they're not going to work with the totals. So that's why if you have a two-way table, you can get rid of a column, so columns minus 1, and rows minus 1. And that tells you you have 4 degrees of freedom. So that's why the formula is row minus 1. You can throw out a row of data and throw out a column of data. And since you have the totals, you can work backwards and figure out what the row was and what that column was that you threw out. Okay, so that's that. Now we can conclude we would say, that since our p-value is very small, less than alpha, would we reject or fail to reject? What do you think, Luke? Reject or fail to reject?
Reject.
Yeah, we would reject the null. And Kenny, do we have evidence or not of a difference in the color distributions? We do. We do have convincing evidence. That the two brands have different color distributions. There we go. So concluding is the same that we've done up till this point. Same thing. So what I'd like to talk about next, I'm going to have to erase that because I'm going to need some space. Well, I guess I try to work around it. I'd like to see what's different between the goodness of fit test yesterday and today's homogeneity test. So there are several differences. So we'll just try to organize it in a table like this. So any ideas? Differences? Perfect, yeah. So a goodness of fit has like one sample, or you could say it's a one-way table. And homogeneity has two samples, and it's a two-way table. That's a pretty big difference. Like if you see a two-way table, if you see something that looks like this, like that two-way table, it automatically tells you what type of test to use. You're going to use chi-squared test, and it's not goodness of fit because there's too many rows and columns. And then what other differences are there? Anything else you can think of? Perfect, yeah, degrees of freedom. For goodness of fit, it's the number of categories that you have, minus 1. And for homogeneity, it's that formula, the row minus 1 times column minus 1. R for row, C for column. So the degrees of freedom is different. They both have minus 1 in them. So they are kind of similar, but they're different. Anything else? Good, yeah, the calculator stuff. So this one uses chi-squared GOF, whereas this one just used chi-squared test on the calculator. This top one uses lists, whereas the second one, the one we learned today, uses matrices. So that's a pretty big difference. And then the last difference is the expected count is n times p, an expected count for goodness of fit. Whereas the expected count for homogeneity is the row total over the table total times the column total. Now, in a sense, they're actually really similar formulas because if you did the row, like we did earlier, if you did the row total divided by the column total, that gives you a percent. So you're kind of doing the same thing. You have the percent times the number in the sample. Here's your percent times your number in your column. So they actually are really similar ideas of how to calculate that. The last thing I wanted to do, but we're running out of time, but I'll do it in a class and I'll end this video. But the last thing I just wanted to make sure is that you know how to use your calculators. So this last page, I just wanted to make sure you knew how to use your matrix menu. So you can read this question. You don't have to answer all the different parts, but really I wanted to make sure you knew how to use your matrix menu to answer something like C and D. But you can try that on your own. If you have questions from your calculator, you can let me know. So thus ends the video. We'll see if it worked well. And I get a phone call. I thought I was muted. I guess not. Oh, dramatic music to end. That's really smart. I'll have to remember that for next time. Get a call in the middle of class, dramatic music. All right.